Swayam Prabha. Digital India. Educated India.
So in the previous classes, we were looking at a numerical simulation which we call kinetic Monte Carlo of continuous Markov process. The strategy there is to find a time scale or a time interval, and then update the system at each of this time interval based on the characteristic function that qualify or that describes the Markov process. Now we also know that there are many other Markov processes which are jumpy. Okay, or we call them as a discrete Markov process, where the state variable changes in a discrete sense. Examples could be a kinetic reaction, a chemical reaction undergoing a particular sequence of reactions, where the number of molecules of each species changes by an integer variable. Okay, and or if you want to think about Brownian motion on a lattice, where the space is discretized already, so it can jump from one side to another site and nothing in between, right? So there are several such examples where Markov process can be jumpy or discrete. Now we can think about devising an algorithm for solving such problems numerically as well. Our intuition would be that okay, we can do the same thing like what we did for continuous Markov process. You choose a time interval delta t, and then you see what's the probability that the state will jump from one state to the other. And this is okay, but what will happen is, there is no kind of rule, there is no kind of a guiding principle that allows us to decide what the delta t, what the time difference is going to be. If you choose your time step to be very small, no event may actually happen, okay, because it's a jumpy event. Each of them will have a particular rate at which this happens. In a very small delta t, there is maybe no such event happening. So you are basically doing a very redundant simulation of updating system with no change is happening in the system. If you take a very long time step, too many events can also happen, okay, more than one event may also happen. So how do we decide what's the time interval to advance the system is a question. So an alternative strategy for this is, we don't say or we don't prefix the time interval, we set the system to decide what is the time between two subsequent events. Okay, so we want to ask what is the time between two subsequent jump events, and you will see that time interval is not a uniform time interval. It is going to have its own distribution. Okay, now we are basically reposing the question that I want to advance the system in time, but the time between these two intervals are not constant anymore, and what would that be? Okay, so we will show that it is basically again a probability distribution function for the time interval itself. So now if I have an expression for the next event time, and I can actually draw that as a random variable, and I can update my system over those time steps, and then I am very sure that every time I choose a delta t based on this distribution, one event is going to occur, and I also know what is that event is going to be. Okay, so this kind of a formulation is called an event driven Monte Carlo. What we did in the case of continuous Markov process is called a time driven, because you say what the time is and then you execute the event. Okay, that is a normal time driven approach. Here what we are saying is, we are going to ask for a time at which definitely at the end of the time interval one event is going to happen. So we are actually asking the event to happen and accordingly update the time. Okay, so therefore we say that this particular strategy is called a time event driven Monte Carlo simulation. Okay, and in the first part of this class I will show how to derive this time distribution, the time between the events, how that is distributed, and then once we have the distribution function, then it's a very straightforward. Okay, so that's the context of today's discussion. So our strategy is to choose the time for the next event. And this time need not be a constant time, it will have a distribution, okay, and what that distribution is, what is the distribution of the interval. What we are also saying is that from between these two times the event is not doing anything, okay, the event is actually quiescent, nothing is happening, only at the end of this interval one event is going to happen, okay. So therefore we sometimes call this interval as interval of quiescence, that is interval of idleness, that there is nothing happening in the system, only at the end of the time one event is going to happen instantaneously, okay. So that is what we want to find out. So what I will do is I will go to the very definition of jump Markov process, how we define the characteristic functions, and from there onwards I want to look for a distribution of the time interval with which I can choose a time, and at the end of the time I can execute an event, okay, and of course I will say some examples also. So the definition of a Markov process, a jump Markov process is based on the fact that there is some time delta t So if you recall, the way that we define a jump Markov process is that the system is at time t at say state some z, okay, this is the current state. Now in the next time interval t plus delta t, the system jumps from z to x, okay, and we are talking about what is the rate of change of this probability, okay, when delta t goes to very small value, okay, and that is characterized by a function transition probability rate. And then if you look at this jump state between two state x and z, that should be sufficiently larger compared to some small value. When we defined the continuous Markov process, we actually put the other way around, that the displacement from one state to the other state should be very, very small. But here we qualify this as a jump state, there has to be a finite change from the current state to the next state whenever there is a jump that happens, okay. So that is the meaning of this particular condition. So we will rewrite this . So now what I am going to do, what I have done here from here to here is that I have said that x minus z, that is the displacement from current state to the next state, I am using that with a variable nu, okay, and this variable nu has to be larger than or greater than or equal to some small number epsilon, okay. So accordingly what I have done here is I have substituted for x equal to n, that is a state variable right now. Think of this n is a number of reactant in a particular reaction mixture, and then it goes from n to n plus v. This nu is a displacement change from one state to the next state, okay. So I am removing all that x into z into x and then x into n plus v, okay, or n plus nu between time. So what we are saying is, okay, this should be also n. So current state is n and t, and this basically goes to n plus v at time to t plus delta t, okay. We are talking about this particular change, okay, where nu is sufficiently larger than some small number, okay. So we are basically qualifying this particular characteristic function for the jump Markov process as the rate of change of the probability per unit time from n at t to n plus nu at t plus delta t. Okay, that's what this function is. Okay, this is basically going to define the characteristic of your jump Markov process. Okay, so this may depends on the time, it may depend on the current number of states, it also will depend on the displacement also. Okay, it's basically a function of all the three. So now I'm going to define a few more probability distribution functions. Q of so if you look at this particular function, what this says is, given that the state is at n at time t, it will make a jump at t to t plus delta t in the time interval to another state which is n plus v. That's what this means. So now what I am trying to do here is, there are two things involved. One is there is a time and there is a state change. Two things are happening, and I actually want to write this into two sets of probability. One that takes care of the choice of the time, and another one that takes care of the new position or the new displacement. Okay, so if you look at this function q of n comma t, this is the current state, and the way I am writing this notation is n comma t with a semicolon tau, and I am saying I am not worried about where it's going to land. I will only say that what's the probability that the system currently at n comma t in the time interval t to t plus tau, it will actually jump away regardless of where it will end landing, right? So here we say that it is jumping, also landing into a new state. I want to decompose this probability into two probability, one that takes care of the jump probability, another one where exactly it lands. Okay, so we say that q here is, given the state is at n at time t, in the time interval t to t plus tau, in the time interval it is jumping away regardless of where it is. Whereas the other probability w here, which is again defined based on n comma t nu, it is basically the choice of where it is going to land. We say that the process has jumped already in the time interval t to t plus tau, but what's the probability it will land into a state n plus nu. Okay, so basically I can write this w is equal to the product of these two as a joint distribution. Okay, and why we do that is because I want to take this particular function later on and then answer this problem. Okay, how do I choose my time delta t for a jump regardless of where it jumps? Okay, so that's why we are doing this way. Yeah. Why we are saying these are independent? So we are basically saying it's a conditional statement that this choice, what I was saying is that this is a jump, the qualification of this process is a jump process, right? So it has to jump and then it can land anywhere. So it can be a independent event. So okay, so think about this Brownian motion, right? A particle jumps either forward or backward. So you're asking what's the probability in the next time interval it will jump to positive direction or negative direction, right? This can be written as the rate it jumps times what is the probability it will go either forward or backward. So it's a two independent, the jumping and where it lands can be independent quantities. No, that's what I'm saying. It's not a continuous process, it's a jump Markov process. Instantaneously the system jumps. So here you see I am saying between t to t plus tau. Now the issue is in this time interval t to t plus tau, if the system is undergoing some change, that may affect here. But what I am saying is from t to t plus nothing happened. Okay, only at the end of this time something is going to happen. So I am basically assuming independence of these two. This is okay for jump Markov process. If you have a continuous Markov process, there is going to be an error involved in this kind of an assumption. Okay, because the system may continuously change, so you cannot probably decouple like this. So what we can do then is we can write this W n plus V So if you look at this expression, this given the system is at n comma t, it is making a transition at time t plus delta t to n plus v is nothing but delta t times this. Okay, I am taking delta t to be very small, so I write in terms of dt, and that is equal to, so if you look at here and here, I have changed this tau into dt because I am looking at some small time interval dt here. Okay, and this remains the same. So what we are saying is that the probability that the system is going to jump in the next time interval t to t plus delta t to a new state n plus v is given by the jump probability and then the landing probability, where exactly it samples that new space. So now what I am going to do is I am going to define this with another function q of n comma t dt is equal to sum a of n comma t dt. So this jump probability is now written in terms of some constant times delta t, and and then if I substitute here, I will see that w of n plus v n comma t is basically given as two functions. This a here, the function a of n comma t is basically like a rate constant. The probability per unit time it jumps. Okay, this is more like a rate constant, and this is where exactly the system is going to sample a new space after jumping. So if you look at, so what we are saying is this particular function and this particular thing are essentially the same thing with a slightly a different context. So what we are saying here is that this product of these two, it tells me that between time t to t plus delta t, in that time interval, the system jumps and then goes to a new state n plus v. Okay. Now, if I choose different time delta t, many times this function may be 0 because in that time interval nothing might have happened. So many times you do a simulation where there is a redundant process. Okay. Now we don't know how to choose the time. Now what we are saying is we are actually remapping this into another problem where I'm not really keen on looking at any time t, but I'm looking at only whenever there is a next jump is going to happen. Tell me the time where there is going to be a jump after I wait long enough. Okay. So then we redefine another quantity. So this and this are very similar. Only thing we are saying here is there is a time tau. Okay. After we elapse the time tau, there is going to be one event. What is the distribution is going to be? So look carefully here. So this and this are very similar. You can see that I am introducing a new variable tau, and this tau is the next time jump, the time required for the next jump. Until that time tau, the system is not doing anything. It's quiescent. It is idle. Nothing happening. After that time interval tau, the system is actually jumping. So we say that this p of tau v given n comma t d tau is, given that the state is at n, the probability that it will jump, its next jump will occur between time, so let me see this. You got time t here and the system is at n. You are looking at some time tau, so this will be t plus tau, and then I take a small interval which is t plus tau plus d tau. Okay, we are asking the system is going to be idle from t to t plus tau, nothing happening, but in this small interval t plus tau to t plus tau to t plus tau plus d tau, in this small interval the system will make a jump. Okay, and this d tau is very small. So here we did not ask for that kind of a question. We did not ask how long the system is going to be idle. We are assuming the system is continuing to change, but then if you sample the time, there are many time intervals where nothing may happen. So you are basically doing very redundant simulation or redundant update. But here on the other hand, we recognize it is a jump Markov process. Events are going to happen once in a while. Now let me ask how long the system is idle before it jumps. So I am asking a distribution function such that the system is idle from t to t plus tau, nothing happening. The state remains in n up to here, and then in this small interval it makes a jump, and then it lands to a new state n plus v. So that's what this is. So please take a moment and understand the difference between this and this. Here I am not imposing any constraint on how the time should be. Okay, it is assumed to be whatever it is. You choose a time, event may happen or may not happen. Okay, if you choose a very small t here, nothing will happen. If you take t long enough, many events may happen. Okay, and there may be correlation and you may violate the Markov conditions. But here on the other hand, what we are saying is I'm waiting until the next event happens, and I'm asking what is that waiting time. Okay, so therefore we define a new function, a new probability function, that is that the system is at right now at n and stays idle until time t plus tau, and then the jump happens in this small time interval and the system is actually going to n plus nu. Okay, so we are writing a surrogate model for this. Any comments, any questions here? Does it make sense, this kind of reformulating the problem? Now if you recollect here, this is what I was looking for. I was looking for a distribution for the interval at which the time, till which it will be idle, and then the next time, in the next time interval it's going to jump, and that distribution is nothing but this. Okay. So now, if you recollect, I have already defined two quantities, q of n comma t tau, and then this w of omega of these two we have already defined. Okay, so this is about jumping regardless of where it jumps. This is about after jumping where it lands. Okay, these are the two things. So now what we are trying to do is we are trying to write this probability function in terms of these two functions. Okay, so what we are saying is, if you look at this diagram, you can understand what this equation means. First of all, this probability is given by the system has to be idle. Okay, it should not jump in the time interval t to t plus tau. That is this 1 minus q. Q is a probability to jump, 1 minus q is probability not to jump. Over which? Over what? It is between this time interval. Okay, the system is not moving at all. Then after this time t plus tau, this is the rate at which it will jump, and this is the rate at which it will land to a new state n plus v. Okay, so this entire probability is now broken into some region where no jump happens times once it happens, then what is the rate and what is the landing probability. Okay, so this basically is given that the state is at n at time t plus tau, probability to jump in the interval t plus tau to t plus tau t tau. Look, the system remains in same state all the way from t to t plus tau because nothing has happened. Okay, so that's why this function a is defined at t plus tau. Still the state is n. You see, the state is still n even though the time has gone to t plus tau because nothing has happened. Now we are asking, in the time interval t plus tau to t plus tau plus d tau, in that small time interval, what's the rate it will jump? That is this. Okay, now here this one, the state jumped in the interval t plus tau to t plus tau plus d tau, and the probability that it will land in n plus v. Okay, and this is going to be probability not to jump over the interval t to t plus tau. Okay. So from here, so what we have done here is the next jump distribution function we are writing in terms of the probability not to jump, and then jumping in the time interval t plus tau to t plus tau plus delta tau, and then landing in n plus v. Okay. So now what we are going to do is, we'll come back to this equation later. But now if you look at this alone, 1 minus q, this 1 minus q is nothing but the probability not to jump in the time interval t to t plus tau. Okay, that's what this means. Now I am saying this 1 minus q as some q star, okay, just for convenience. So 1 minus q is the probability not to jump, right? So now this is the probability not to jump in the time interval t to t plus tau, right? So now what I am asking is, I am writing what's the probability that it will not jump in the time interval t to t plus tau plus d tau. So if you look at this and this, the only thing I am asking is, here it is not jumping in the time interval t to t plus tau. This function is extending that little beyond, asking what's the probability it will not jump for an interval t to t plus tau plus d tau. That's all. Look at this and this. The only difference I am saying is, I am adding another d tau here. Okay. So this is t, and let's say this is t plus tau. So what is the probability that it will not jump in this interval is given by this quantity. Okay. Whereas here I am extending this interval a little beyond, and I say, so let's say here you have t plus tau. I am asking what's the probability that it will not jump over an interval of t to t plus tau plus d tau. That's what this is. All I have done is I have just added an extra time, small time d tau. So now what I can do is, I can write this probability as the probability it will not jump in this interval times it will not jump in this interval. Again, by assuming that this is an independent process. So you see, this is same as before, that it doesn't jump in the time interval t to t plus tau, and this quantity on the other hand is a probability it will still not jump in the time interval t plus tau to t plus tau plus d tau. Okay, that's this. So if you ask why I am doing this, we will see how we are going to write in terms of this function a later on. So this q star, again I am going back to 1 minus q, okay, because q is a probability to jump, 1 minus q is the probability not to jump. So I have this, and then if you remember the first in the beginning, we defined this q of this into some rate constant times d tau. Okay, I am just substituting that here, and then I am just taking this q star to the left, and then you have on the left hand side you have q of n comma t t plus d tau minus this quantity, and then divided by the same quantity. So this is nothing but dq by q. On the right hand side you have a of n comma t plus tau d tau. Okay, so this has to be integrated now. So when you integrate, you are going to integrate with respect to this tau, the time interval tau. Okay. So now if this time interval tau is very small, near 0, it is very likely that it will not jump. So the probability that it will not jump will be 1. So we take this as an initial condition, and then when you integrate this, you will get an exponential function like this. So now we can substitute q star is nothing but 1 minus q, and that is equal to minus So now we have an expression for 1 minus q, so we can go back and substitute for the next jump density function. So in the term where we had 1 minus q, I am substituting this exponential term, the remaining a's and w's are here. So we can combine these entire thing So if you look at this function alone, okay, what do you see? Some a times e power minus integral of this a. So this entire thing depends only on the next jump time, which is tau. Doesn't depend on the where it lands. Whereas this function depends only on where it lands, because the jump has already happened at time t plus tau. Okay. So now we can write this into two probability distribution functions. So we call this entire thing as P1, which allows us to choose the next jump time, and P2, which is the choice of the new state nu. So therefore we are saying that P of tau nu n comma t is equal to P1 of tau n comma t and P2 of nu n comma t plus tau. If you remember, when we looked at this random number generator, the normal random number variable, the Box-Miller method, so our aim was to generate a normally distributed random number. But if you remember, we actually wrote that as a product of two distribution functions. One, an exponential distribution function, and another one as some uniform distributed function. Okay, the product of that two gave the normal random variate. In the same way here, we want the next jump time, which is tau, is actually decomposed into two different kind of probability distribution function. One takes care of this choice of the tau, another one that takes care of the choice of the new state, the next state. Now this variable become a little easier if you say that you have a homogeneous process, meaning that this a of n comma t, if this simply becomes a of n, if it doesn't depend on time. Okay. So then what happens is P1 simply becomes a of n into e power minus, so this a will come out of the integral, so you will get a of n comma tau, and this is nothing but an exponentially distributed random number. Okay, so that means the next jump time tau is an exponentially distributed random variable. Okay, so the question I posed in the beginning was, what is the time at which the system is idle and beyond that the system makes a jump? That time interval is actually an exponentially distributed random variable whose rate depends on the rate constant a. Okay, and this one is your so once you choose your tau, the interval from this distribution, then you can choose the new state nu based on this particular function. Okay, So when I say homogeneous, what I meant was this function a and omega, these are all independent of time, so that you can show that the next jump time is an exponentially distributed random variable. Once you choose tau from here, you can advance the system based on this function. This function has to be again defined by us. It depends on if it's a Brownian motion, nu can be either +1 or -1. If it's a Poisson process, nu can only be +1. If it's a chemical reaction, nu can be only -1. So here, this is where as a modeler, we have to define how the state change is going to look at it. Okay, what are the possible states the system can jump to? Sometimes we may have many processes happening. Okay, there could be many possible values of nu. So then we have to define this distribution function. Okay, so we'll stop here. We'll take it in the next class, the algorithm to solve this kind of problem, and with some examples of how to choose this one and how to choose this a and all that. Okay, so I have given all the entire derivation in my class note. So take a look at it and then follow the derivation. Okay, I'll stop here.